Welcome, my friends. I'm so excited because in this video, we get to talk about the hypothesis test for two independent means and two independent proportions. So let's go ahead and get started. Let's begin by discussing the two independent mean hypothesis test setup. The purpose of this test is to compare two independent means, such as the mean between individuals in two different countries, or maybe two different schools, or two separate groups that you want to somehow compare the mean for. First, we could have what is called the left tail test, meaning that you believe that the first mean is smaller than the second mean, which would relate to a p-value in the left tail of the distribution. You could have the right tail test, which would amount to you believing that the first mean is larger than the second mean, which would amount to a p-value in the right tail of the distribution. Or we could have the two-tailed test, which would be saying that I think there's somehow a difference between these two means, but I'm not really sure which one is larger. And that would amount to finding a p-value that would be in both tails of the distribution. Now, the assumptions for this hypothesis test are, of course, you must have random samples from your two independent populations. You also must have sample sizes of at least 30 for each of your populations, or if that's not the case, then the variables should follow normal distributions, and that's so that the central limit theorem applies. And then number 3, the populations are not assumed to have equal variances, at least for the test that we're doing. This is called the unpooled variance method. There's a different method that assumes equal variances, and that's called the pooled variance method. If we were to do this hypothesis test by hand, we would end up having to find a test statistic using this formula here. And as you can see, the formula is a little bit complicated. So due to the calculation-intensive nature of the test statistic formula, and also the degrees of freedom, which have a not so straightforward formula, it's no longer just n-1, we're going to be using a TI-84 calculator function to help us complete this test. This above formula is what the TI-84 function is going to do. So basically what you will do is provide the calculator with your two sample means, your two sample standard deviations, your two sample sizes, and it will calculate this for you. So let's go ahead and take a look at an example. So we want to see if pizza shop number 1 or pizza shop number 2 takes longer to deliver pizza to your house on average. So if you want to get pizza as fast as possible, should I go with the first place or the second place? You know, they might be similar distances away from you, but one of them might be faster, and you want to figure that out based on a sample. So you take a sample of 40 deliveries from the first place, and you got a mean of 37 minutes and a standard deviation of 6 minutes. And from your sample from the second place, you had 43 deliveries, and you had a mean of 40 minutes and a standard deviation of 4 minutes. You want to know if there's sufficient evidence to suggest that pizza shop number 1 is delivering pizza faster to your house on average than the second pizza shop. So the first thing you should do is write out some of the given information. We had a sample size of 40 from our first pizza place, and we had a sample mean of 37. That's going to be x bar. And then we had a standard deviation of 6. That's going to be our s. From the second location, we had a sample size of 43, and we had a mean of 40, and we had a standard deviation of 4 minutes. So already we can see, based on the sample means, it does appear that the first pizza place is a little bit faster than the other one, but it could be just due to chance that we got a slightly smaller mean here, and maybe if we did another sample, it could be the other way around. We want to determine if this is definitive evidence that we really can state that the first pizza place is faster than the second one. So the first step is to set up our null and alternative hypotheses. And once again, I will refer you back to the handout that I've looked at in previous videos here. We're doing the third row here for two independent means. And our null hypothesis is always just going to be that those two means are equal to each other. So that's what our null hypothesis is going to be here as well. Our alternative hypothesis is either going to have a less than, greater than, or not equal to sign, depending on what we are suggesting in this problem. And in this problem, they say, is there evidence to suggest that the first pizza place is delivering pizza faster to your house than the other one? Be very careful here. Faster actually means less time. And since our variable relates to the time, delivering faster is going to be like a smaller mean, right? Less than. So we're going to have a left tail test in this case. Now at this point, you would go ahead and you would plug into that formula that I showed you from earlier, but like I said, we're going to be using the TI-84 calculator to do this. So what you can do is you can go to Stat, you can arrow over to Tests, and then we're going to use the option 4 here, which is the two-sample t-test. Now you have the option for either data or stats. If you choose stats, you will be prompted for kind of these input numbers that we already have written down. Otherwise, data, you could have put the data in your lists. But we don't have the data, so we have to do the stats. So we have x bar 1, which is 37. We have s1, which is 6. We have n1, which is 40. So that's our information for the first sample. And then the second sample, we have an x bar of 40. we have a standard deviation of 4 and a sample size of 43. Next, this is asking for our alternative hypothesis. So in this case, we have the less than, so we're going to choose that second option, press enter over that. Next, we can scroll down. It's going to ask us if we want to use the pooled method. I already mentioned the one that we're going to cover is what's called the unpooled variance method. And that just says that, in the population, we're not assuming that the two populations have equal variances. So we're going to choose no there. We can either calculate or draw. I'm going to go ahead and calculate, and it's going to give me the information that we need. So it gives me the t-score, the p-value, the degrees of freedom, and some other things. Really, the main two things I'm going to be asking for are the t-score, which would be what you would get from that formula if you would have plugged into that formula, and then also the p-value. The p-value is really the most important, but we'll also write down the t-score as well. So here I have that information in the slides here, some instructions as well as that output. You could also visualize this on the distribution. So we had a t-score of negative 2.66, and that p-value is really the area to the left of that since we had a left tail test. We don't really have to use any special function like tcdf to find this because the calculator actually gives that to us right here. So this is our p-value. So really at this point, we are ready for our step 3, which is decision and conclusion. To make a decision, we have to compare the p-value to our level of significance. And in this case, our p-value of 0.0049 is less than or equal to our level of significance. So you may remember the saying, if the p-value is low, the null has to go, which is the case here. So the p-value is less than or equal to our level of significance, so we are going to reject our null hypothesis. The only thing left to do would be to write a concluding statement. So here I have the general template for that. At the alpha % level of significance, in this case, the 5% level of significance, there either is or is not enough evidence. We're going to say that there is enough evidence since we rejected the null hypothesis, right? So we say there is enough evidence to suggest, and then we're going to describe our alternative hypothesis. Our alternative hypothesis is that the first mean is smaller than the second, so that's what I'm stating here. Pizza Shop 1 is delivering pizza faster to your house on average than Pizza Shop number 2. And really, that's all there is to this type of problem. So it's a little bit maybe simpler than the one sample cases when we were using the formulas. Using the calculator does speed things up a little bit, not quite as much work to do in that second step. All right, here is a problem for you to try. Among music majors, do pianists or violinists practice more hours per week? The weekly practice time from a random sample of 12 piano performance majors and I think I should say and, fixed, and 9 violin performance majors is shown below. Is there enough evidence to suggest that either piano performance majors or violin performance majors practice more in the population? We're going to use a 5% level of significance, and we have to assume normal distributions because we don't have a sample size at least 30. So the difference with this one is before we had the actual statistics, but here we do not. We just have the actual data. So instead of writing down the data from the information in the problem, you would want to plug this data into your stat list. So plug the pianist information into list 1 and the violinist information into list 2. So you would go in there, I'm not going to do it right now, but you go to stat, enter, and then you would plug in the numbers there. And then when you eventually went to stat and went to tests, option 4, you would have to, in this case, say that you have data, and you can put list 1 and list 2 in there. Should probably default to that, or you can press second 1 or second 2 for list 1 or list 2. And we don't need to change the frequency. We can just leave those at 1, and then you can select your appropriate alternative hypothesis, and you'll get the answer. Go ahead and set up your hypotheses. I would still start with step number 1. Write down your null and alternative hypotheses. Then go to the calculator, plug all these numbers into your lists, and then run the test. Get your p-value and test statistic, and then make a decision, and finally write a conclusion. Okay, so pause the video and give that a shot, and then we will move on to the next test. So the next test here is going to be for 2 independent population proportions, and I put these in the same video because they are very similar to each other. So now instead of comparing a mean for 2 different populations, we're going to just compare the proportion. So we're still going to have left, right, and two-tailed tests, but now they're going to be related to p rather than mu. So the left-tailed test would be equal to and our null hypothesis for our 2 proportions we're comparing, or less than and our alternative. We'd end up trying to find a p-value in the left tail. We could have the right tail test where we think the first proportion is larger than the second with a right tail test. So we're finding a probability in the right tail. Or the two-tail test where we had the not equal to, would be finding the p-value which is split between the 2 tails. So here are the assumptions for this test. We should have a random sample from each of our 2 independent populations. A whole bunch of quantities should all be at least 5. And to calculate that p-bar value that you see there, you'd have to take the combined total number of successes and divide by the total of your sample size. and also you have Q bar, which is 1 minus P bar. Honestly, I'm not going to ask you to check this here, probably, most likely if you're in my class, but I just want to mention there are these assumptions here, and technically if you wanted to check these, you'd have to use some of these values. All right, here is the test statistic formula. If you were to do this by hand, we're not going to do it by hand, but if you were, then you would have to use this formula here for a z-score. And you'll notice that p-bar value is there again. P-bar is kind of like saying, pretend everything came from one sample and calculate a sample proportion from everything, right? So I have two separate populations I've drawn from. Just pretend they all came from one sample and find the proportion. That's what p-bar is. And then the p-hats would be specifically for each of the populations. So due to the calculation intensive nature of this, it's a little bit of work to do this, and really the focus here is not the calculation, it's more on the interpretation and understanding what's going on with the hypothesis test. We're going to be using a TI-84 function to do this instead. So let's look at an example. So a 2021 YouGov poll asked both Americans and Brits, which of the following animals, if any, do you think you could beat in a fight if you were unarmed? So kind of a comical little survey here, and the percentages are listed below. So we have anything from the rat, the house cat, the goose, the medium dog, the eagle, the large dog, the chimp, the king cobra, the kangaroo, the wolf, the crocodile, the gorilla, the elephant, the lion, and the grizzly bear. And we have what percentage of individuals thought they could win in this fight if they were unarmed. So, disclaimer here, your teacher does not, condone fighting against animals. This is just kind of a funny survey that was done here. And we have all these percentages. So, compare between Americans and the Brits here. We have quite a difference here. The Americans are consistently seeming to be quite a bit more confident, right? So we have, every single category, it seems like the Americans are more confident. So apparently 8% of Americans think they are somehow taking on this lion or elephant, right? I'm not really sure what their plan is, but apparently about 8% of individuals are thinking they can win against a fight from, some of these very dangerous animals. But let's go ahead and focus on the closest category. The closest category is the house cat, right? 69 to 66%. And we want to know if there is sufficient evidence to suggest that more Americans think they could win in a fight if they were unarmed against a house cat than people from Great Britain. Now, of course, it is higher in the sample, but we're trying to talk about more about the greater population of all Americans and people from Great Britain, right? The whole point of hypothesis testing is not to just focus on the sample, but try to extrapolate to the population. That's what we call inferential statistics, right? So yes, we do know, and we can see here that Americans were more confident in this sample, but we want to know if this is good enough evidence for us to really more definitively say that this trend also is the same in the population of all Americans and people from Great Britain. So I grabbed some of the information from this survey. This is a real survey, and the information said that there was 845 Americans out of the 1224 surveyed, and 1374 of the people from Great Britain out of the 2082 surveyed believed that they could win in a fight against this house cat if they were unarmed. And we want to know if this is good enough evidence to suggest that the proportion of Americans who think they can win in a fight against this house cat is greater than that of people from Great Britain. So our first sample is Americans. We had 845 successes, so we use X1 to represent that, out of a sample size of 1224. From Great Britain, we had 1374 successes out of a sample size of 2082. We could go ahead and calculate those p-hats, but it's not really necessary in this problem because the calculator will do that for us. We can really just go and set up our hypotheses. So once again, if you're stuck with the hypotheses, you can always look at the sheet and you can see that the null hypothesis is that your two proportions should be equal to each other. So we can write that down for our null hypothesis. The alternative is going to have a sign in the middle, either greater than, less than, or not equal to. In this case, we want to test to see if the Americans are more confident. So we would put the greater than sign there. And at this point, we would be ready to go to our calculator. So we can go to stat, arrow over to tests. Then we can scroll down to the 2-prop z-test is the option we want here. 2-proportion z hypothesis test. And once again, some of these instructions are here on this sheet. So we can see it just says use TI-84 for the test statistic, stat, arrow to tests, and 2-prop z-test. Same thing was true for the 2 independent means test. You got the instructions here. And then the p-value, I did just want to put in the p-value, how the p-value would be calculated for each of these. You would use TCDF or normal CDF, although in most cases we're not going to need to do that because the calculator procedure is going to generate the p-value for us. So once we're here, we can go ahead and plug in the numbers, 845 for our x1, and our n1 was 1224. And then we had, for x2 was 1374, and n2 was 2082. And then we can go ahead and select the correct option here, which is greater than. So we have greater than, which is the last option to the right. So we can select that, and then we can go down to calculate and press enter, and it's going to give us the p-value. One thing I just want to mention here that a few students have sometimes mixed up. If you would have had a two-tailed test, then traditionally in the one sample case, we'd usually have to multiply our p-value by 2 to get the answer. But that will not be the case here. So if you were to go in here and select the 2-prop z-test and choose the not equal to, you're basically telling the calculator you're doing a two-tailed test. So if I was to select that option, when it reports the p-value, it's already reporting the two-tailed p-value. So make sure you don't make that mistake. If you're ever using the 2-prop z-test or the whatever the other one's called, the 2-samp t-test. If you're using either of those options, if you choose the two-tailed option, you don't need to multiply it by 2. The calculator's already done that for you. But it doesn't really matter here because we have the greater than, and our p-value in this case was 0.0361. Here's the z-score if you would have plugged into that formula that we looked at from earlier. So here's some of that output on the slides. And then you could also envision that on the distribution here. We had 1.8 as our z-score, and we had a right tail test, so that p-value in the right tail is 0.0361. So we can go ahead and we can make our decision and write our conclusion. So we'd make our decision by comparing our p-value to the level of significance. Our p-value is 0.0361, which is less than or equal to our level of significance. The p-value is low, so the null has to go. So we are going to be rejecting our null hypothesis. And finally, we can go ahead and we could write our conclusion, which is using this general template here again. So we would say at the alpha percent level of significance, in this case 5%, there either is or is not. Well, we're going to say that there is enough evidence, right? There is enough evidence since we rejected our null hypothesis to suggest that the alternative hypothesis, which is the proportion of Americans who think they can win in a fight against this cat, is greater than that of Great Britain. And that would be the end of the problem. All right, so here is one for you to try. A political campaign wants to decide or determine if there is a difference in the proportion of voters who prefer their candidate for male versus female voters. So like there's this candidate that they are supporting, this campaign, and they want to know, is there a difference between the proportion of males versus females who support this candidate? To test this, they survey 300 male and female voters and find that 170 males and 140 females support the candidate. So once again, we see a difference here between the males and the females. But we want to know if this is a definitive enough difference for us to really be able to make that conclusion also in the population. It says, test to see if the result of this sample provides sufficient evidence to claim that more males in the population support this candidate than females at the 5% level of significance. So start off by writing out your null and alternative hypotheses and also the given information. Write down the symbols that are related to some of these numbers. Go to your calculator and run that 2-prop z-test, whatever it's called, right? Run the 2-prop z-test function, and then you will get your p-value and test statistic. From there, make a decision to either reject or fail to reject your null hypothesis, and finally, write a concluding statement. All right, I think that is all I wanted to talk about in this video related to the 2-sample hypothesis test. So hopefully you found it useful, and I will see you in the next video.